So for this question here, the first thing that you should realize is, first of all, the n will mean the same value for both. If you have to get something closest to 2,000, you've got to be thinking in terms of powers of 10 that might be close to the thousands. So that alone narrows it down to 10 to the 2, sorry, 10 to the 2 is 100, so that's not going to be right. So it narrows it down to 10 to the 3, which is 1,000, or 10 to the 4, which is 10,000. Those are the only things that are going to be kind of reasonably close to 2018. Then you've got to compare what's 5 to the 3 and what's 5 to the 4. You just do a quick mental subtraction. This one you're going to end up with 875. This one's going to be well over, like this one's going to be almost 10,000 to be perfectly honest. So which one's going to be closer to 2018? It's going to be this one right here. So n is going to be 3. So if we look at the next problem, this is really kind of like a combinations type problem. And the best thing to do is to follow a systematic approach. So for example, I can make a triangle from A to B to C. Then systematically, I can go A to B to D. Then I can go A to B to E, and so on. Then I can go, and I would go through A, B, C, A, B to D, A, B to E. Then I would go, I don't know how many more colors I have, but I'd go B, C, D, B, C, E, B, and I would keep repeating, and I would go in a systematic order. And if I follow a systematic order, I'm going to end up with A, B, C, A, B, D, A, B, E, A, C, D, A, C, E, B, C, D, B, C, E, B, D, E, and C, D, E. And in total, I'm going to have 10 different triangles that I could make. For those of you in the Enrich class that remember the Harvey's problem that we did at the beginning of the year, this is also very similar to that because we have 5 objects and we're choosing 3. The triangle is 3 vertices. Just like in the Harvey's problem, how we had, I don't know how many it was, 28 toppings and we chose a certain number. Very similar idea. And there is a formula, NCR, which is the choose formula. And we did look at this briefly when we looked at the Harvey's problem, so that's an N. Where N is how many objects you have, and R is how many you're choosing. So in this case, N would be 5, and R would be 3 because we have 5 objects and we're trying to choose 3 of them. So that's something else that would work for this problem. It connects in with probability and things. This is formally, you would be learning this, I think, in about, I think it's in grade 12, data management maybe that you're introduced to this concept. This one here, so we have terms in the sequence and they give us some of the numbers and you basically take the digits and cube them to get the next. And so we could look at just continuing the pattern. So for example, if I'm at 133, 1 cubed plus 3 cubed plus 3 cubed will end up giving me 27, 27, and 1 will give me 55. And then 55 cubed, 125, 125 will give me 250. And then 250 cubed, that will be 8 and 125 will give me 133. What I'm going to then see is, hey, I got 133. Oh, I go back to here. And then this is just going to become a repetitive circle that just keeps moving on and keeps moving on. So what you notice is it goes 265, 349, 825, 20, 133. And then it goes 55, 250, 133, 55, 250, 133. And it keeps repeating. So basically, there's 4 here that aren't part of the pattern. So if we have 100 terms, we really, if 4 aren't part of the pattern, we have 96 terms that will be part of the pattern. And then the pattern has 3 things that repeat in it. So 3 goes into 96 32 times, exactly, no remainder. So that means there'll be exactly 3 cycles of this 133, 55, 250, 133, 55, 250. Because there's exactly 32 cycles, the last term in that cycle is 250. And that's the answer. So this one here, they give you the prime factorization of both numbers. And so if you know that 2016 is 2 to the 5 times 3 to the 2 times 7, and 2018 is 2 times 1009, then 2016 times 2018 is just going to be those things multiplied together. Then we can simplify because we've got 2 powers of 2 there, so it becomes 2 to the 6 times 3 squared times 7 times 1009. So now you had to come up with the number of divisors. So the interesting thing is you always have one more divisor than the power. So for example, 2 is like 2 to the 1, but the number 2, I have 2 divisors, 1 and 2. 3 squared, that's like 9, but 9 has 1, 3, and 9. So I have 3 divisors. So you always have one more divisor than the power. So keeping that in mind, this is going to have 7 divisors because the power is 6 plus 1. This one will have 3. This one, because it's 7 to the 1, will have 2, and that's to the 1. It will also have 2. So then all you need to do is multiply those numbers together, 7 times 3 times 2 times 2, and that will give you 84, and that's how many divisors you would have. You could have like broken this down into kind of a factory, that kind of idea, but really this is a lot faster to be able to get to the answer. This one here was a little bit challenging for many of you. One of the first places that you could start, if you know this, you know that's really the same thing as saying that 1 must be between n and 49. Because to get rid of a square root, we square it. And 1 squared is 1, and 7 squared is 49, and the square root of n squared is n. So keeping that in mind, we know that we have to find a value of n that's between 1 and 49. Then we're going to look at different scenarios. So we have a scenario where statement 1, statement 2, and statement 3 can be true, and 4 is false. We can have a scenario where 1, 2, and 4 are true. We can have a scenario where 1, 3, and 4 are true. And we can have a scenario where 2, 3, and 4 are true. So if we look at statement 1, 2, and 3 being true, we have to consider how many numbers between 1 and 49 might that happen for. So we have to think about something that is prime and has n plus 3 that is prime. But after you get to 2, so 2 is a prime number, but after that, all other prime numbers are odd. And anytime you add 2 prime numbers together, you get an even number, which will not be prime. So the only answer that works for 1, 2, and 3 to be true is 2. So 2 is prime, 2 plus 3 is 5, which is also prime, and it's between 1 and 49. If we look at the last statement, 2 plus 7, 2 plus 5 is 7. 7 has 3 factors. 7 has 2 factors, 1 and 7. So all prime numbers have only 2 factors, 1 in themselves. So we have one number so far that works. So now we look at the second statement where we have, it has to be prime, it has to be, the number plus 3 has to be prime, and the number plus 5 has an odd number of factors. So because n equals 2 is the only thing that will work for number 1 and number 2, but if we put 2 into here, 2 plus 5, we get 7. As I just said, 7 has only 2 factors. So 1 and 2 work, but number 4 won't. So there's actually no number. My pen's not working now. Okay, I'm just going to pause the video while I see if I can get my pen to work. Okay, so there are no numbers that will work for, because again, if I repeat that, the only number where number 1 and number 2 will be true is the number 2. But the number 2 is not true for statement 4. And because all 3 have to be true, then there aren't any numbers. So now we can look at 1, 3, and 4. So for this one, for a number to have an odd number of factors, that would be statement 4. It has to be a perfect square. So think about it for a second. Most numbers pair up when you factor them. So for example, if I had 8, I would have 1 and 8, and I would have 2 and 4. So numbers always pair up when you break them down into their factors. The only thing where numbers won't pair up, so if I had something like 9, I have 1 and 9, but then the middle is really 3 times 3, so that's only one factor. So all perfect squares have an odd number of factors. Anything that isn't a perfect square always pairs up and will have an even number of factors. So we know that we have to have a statement for number 4 that creates a perfect square. So we have to think about numbers that are actually, so this is n plus 5. So we have to think a perfect square take away 5 to think in terms of numbers. So perfect square is between 1 and 49. We've got 1, but that won't work. We have 4, but 4 minus 5 gives us a negative number, so that's not going to work. We have 9. 9 minus 5 gives us 4, but 4 isn't prime. 16 minus 5 gives us 11. Oh, well, 11's prime. And 11 plus 3, sorry, not statement 2, but that was it. I just need to prove statement 1. So 11 is prime. 11 is one that works. My next perfect square is 25. 25 minus, my next perfect square, yes, 25. 25 minus 5 is 20. 20 is not prime, not going to work. My next perfect square is 36. 36 minus 5 is 31. 31 is a prime number, that's going to work. And then my next perfect square is 49, but it has to be between 1 and 49, so I'm done. So there's exactly 2 numbers that will work if those 3 statements are true. Then I need to look at the last statement. So I need to have statements 2, 3, and 4 to be true. So again, for statement 4 to be true, I know that it has to be 5 less than a perfect square. But in this case, instead of the answer being prime, the answer plus 3 needs to be prime. So if we go back to, we started with 1, remember 1 didn't work, 4 didn't work, 9 minus 5 is 4. 4 plus 3 is prime, so 4 will work. Then we have 16 minus 5 is 11, but in this case, 11 plus 3 gives us 14. That's not prime. It's not going to work. Then we have 25 minus 5, which is 20. 20 plus 3, that is prime, so 20 will work. Then we have 36 minus 5, which is 31. 31 plus 3 is 34. That's not going to work. And then if we try 49 minus 5, we get 44. But 44 plus 3 is prime, so 44 will work. So we have 3 numbers that will work there. So we have 2 numbers, 2 numbers, 3 numbers, for a total of 6 numbers where exactly 3 of those statements is going to be true. That one was a little bit complicated. Hopefully you followed it. If not, just come and talk to me. I'm happy to go through any of these solutions with you and help you to develop your problem solving.